There we go. Hello everyone. Today we've got Uğur giving a talk on persistent homology. So I'll let you go ahead.
Okay. As a first thing, thank you. And it's a great pleasure to be here. Today I will talk about persistent homology, but as a first thing, let us consider the general perspective, which is topological data analysis. It just uses topology to study the shape of data. Here, our data can come from different types. As a first one, it can be a finite set of points in some Rn or any metric space. And also we have start with some function from some compact topological space to some Euclidean space. But in here, finite, and compact, generally, and we just encounter with our practice worlds in our real world. But in our theory, it can be generalized to infinite case and also non-compact case. And persistent homology is just the most widely used method in TDA. Now, let us try to understand the idea behind persistent homology. Let us say we have discrete set of points in Rn, and we are trying to understand the shape. What I mean, for example, we can just try to understand whether there is a zero-dimensional hole, one-dimensional hole, etc. And we have homology, which is an algebraic tool, actually tool in algebraic topology, let me say, to detect holes of a topological space. But as you can see, this is discrete set of points. So if you just apply a homology where your degree is bigger than or equal to 1, then you will obtain nothing special, just trivial solutions you will obtain. And in terms of zero homology, you will just obtain the number of connected components. But as you can see, that is just the number of your points. So you are not obtaining any interesting results. So persistent homology suggests that instead of your discrete set of points, just consider the thickened version. So from low dimensional, let me say, structures, we are just trying to obtain something general. And here, thickened version means we are just considering some closed balls where our centers are just our given points and our, let me say, radius is just depending on a scale parameter epsilon. And for example, in this case, let us say we are in R2 and we just obtain a thickened version. And on the right-hand side, now we have a one-dimensional hole. And we cannot see something like that on the left. So with this argument, now we are obtaining some interesting results. But as you can see, we just specified and fixed some epsilon, and we just looked for a single topological space. Persistent homology has some problems with fixing epsilons. So it just says that instead of fixing an epsilon and looking into a topological space, a single topological space, we just consider all of the possible epsilons. We will consider all of the possible topological space because we have the following problems. There is no the best epsilon, and we are not looking for that. And as a second one, if you just perturb your set of points or your scale parameter epsilon, then the corresponding topological space will differ a lot. So that's the main problem. And as a third, we cannot distinguish big holes and small holes from each other. This big and small means in terms of importance, let's say. So persistent homology suggests that we are considering all of the possible epsilons. So for instance, we just start with a discrete set of points and we are just increasing our epsilon, our scale parameter. And as you can see, in whole of the way, your topological space is getting bigger and bigger. And somewhere you are obtaining some higher dimensional holes. And this hole, for example, this hole just disappears in the last, actually in this stage. And also another hole appears and it just leaves at some time, let me say, for some time. So these inclusions between these topological spaces just creates something new, which is called filtration. We say a filtration indexed by natural numbers is just a nested sequence of topological spaces. As you can see, we are starting from K0 and we have some inclusions until Kn. Here, n is not necessarily finite. And to see a better example, we are considering Vietoris-Witt complexes, which are just actually simplicial complexes, depending on a parameter as well, epsilon. Here, the K-simplex of our simplicial complex is just made of unordered K+1 distinct points, such that all pairwise distances is smaller than or equal to epsilon. So if you see 2 points have a distance smaller than or equal to epsilon, then you are drawing an H between them. For instance, in this example, as you can see, we just start with epsilon equal to 0 case. And when we increase epsilon, we are getting bigger and bigger in terms of topological spaces. And in here, for example, the distance between these 2 points is something smaller than or equal to 0.6. So we are drawing an H. And similar for the higher dimensional simplicial simplexes. And as you can see in 2.1 epsilon value, it is just full disk. So from that value, we don't need to increase our epsilon values because it is just full right now. So we don't need something else to consider, something more. And here, to detect the lifespans of homology classes, we will consider the induced maps. What I mean, if your I is smaller than or equal to j, then you have an inclusion map, right? Ki to kj. And then this map induces a homomorphism in homology groups in the pth dimension, let's say hp ki to hp kj. And if you consider the whole of the filtration, then that filtration will induce a sequence of homology groups, as you can see in here. So intuitively, we can say it like this. We have a sequence of topological spaces, and we are just applying homology factor to that filtration, and we are obtaining a sequence of homology groups. And now we can define P persistent homology group from I index to J index as the image of that map. We have inclusion map, and that map just induces another map in terms of homology groups from HPKI to HPKJ. And by looking at the image of it, we can just say that this is P persistent homology group. And intuitive idea is just as follows. Let us say we have some homology class living in here, and we are trying to understand where it goes actually, whether it is also living in here or not. And with the help of this map, we can say that whether this our former, let me say, homology class is still in here or not. And after a meaningful summary, we are trying to obtain some complete invariants over there and some meaningful summaries, let me say right now. And the ranks of those maps is just those images, let me say, is just called as P persistent Betty numbers. So we are just tracking homology classes, whether it is still in here or in here as well. Now, we want to use some algebraic definitions and algebraic, let me say, theorems to obtain some meaningful summaries. Now, let me define a persistent module. We are saying it is as M, and it is indexed by T. Here, T is just total ordered set. It is just a collection of R modules showing like this, M sub i's. Here, it is just have some indexes, M sub i's. And as you can see, this is something familiar. We have K sub i's, K sub j's as indexes. And here, this is just the applying, this is something after we, actually, this is something we obtained after applying homology, let me say. And here, R is just a commutative ring with unity. So you can consider it like as a collection of R modules with some indexes. And indexes are coming from total ordered sets. And if I is smaller than or equal to J, then you are obtaining a homomorphism between these two R modules. And we need to satisfy these two conditions. If you are going through I to I, then it must be an identity map. And it has the transitivity, yes, argument, let me say. And we can just consider a class of persistent module, which is called as finite type. And it has this property. Each M sub I is just a finitely generated R module. And each map Phi from I to J is an isomorphism after some M. So there exists an M. And if we just pass through that M, then your indexes, if just passes through M, then your inner homomorphisms are just isomorphisms. So this is something a part of our general persistent modules. And here you can be suspicious about, yes, we have some indexes. Maybe we can see these persistent modules as graded modules. And that is the main argument of defining persistent module. Yes, we are saying that module, but as you can see, right now we cannot see any module structure, and we will put that structure by considering graded module arguments. And now we can define a multiplication over here, and that multiplication shown by x is just a one shift upward in grading. That means if you just multiply x with m0, m0 is an element of m0, big M0, then it just goes to the next one, x of m0, as you can see, with the map which we defined earlier, the inner homomorphism. And similar for m1, it just goes the next step, as you can see, from 1 to 2. And with the help of this map and defining a new map from M to the direct sum of each component M sub i's, we can see our persistent module as a graded module. But here, this is persistent module over R, let me say. And on the right-hand side, we have a persistent module over Rx, which is a polynomial ring with coefficients from our module R, not module, sorry, ring R. And the theorem of one of the main theorems, Carlson and Zamorodyan, says that there exists an equivalence between two categories. The first one, the persistent modules indexed by n of finite type. What was finite type? After some m, all of the inner maps are just isomorphisms, and each spot M sub i's are just finitely generated R modules. Yes, the category of persistent modules indexed by n of finite type over R, and the other type is just the category of finitely generated non-negatively graded modules over Rx. So we can see every persistent module as a graded module. And now we have a well-known theorem in algebra, which is called structure theorem. And we are trying to use this structure theorem. And it says that every finitely generated graded module, yes, we know we obtain something like that, over a graded ring, but this graded ring D must be a PID, decomposes in the following way. As you can see, the left-hand side is just the free parts, born somewhere and just lives forever, let me say. And on the right-hand side, we have some torsional parts. I will not go into detail of this theorem, but let me just go back. Here, as you can see, we have finitely generated non-negatively graded modules. Okay, finitely generated graded modules. And this is in the beginning side of this theorem, but we must satisfy this D as PID. But in our case, D is just Rx. But if you just choose your ring as integers, then Zx is not a PID. So you actually we cannot use this theorem in all cases. We need to obtain our Rx as PID, and if you choose your R as a field, then you will obtain Rx as a PID. So you can use this theorem. So that says that your persistent module of finite type can be decomposed into the following way, with some torsional part and with some free part. So that says your homology class somewhere just borns and it lives forever, and for the right-hand side, for some finite lifespan. So this is something very powerful, and we can ask ourselves that yes, this is true for finite type, but what about the general case? For example, yeah, it must be in here. For example, for 0.5 finite dimensional case, if you say, actually, let me define 0.5 finite dimensional case. Each dimension of M sub I must be finite, as you can see in here. But let me just go back in here and tell all the story about this. We obtain some free portion and some torsional portion. Yes, I know. And to obtain a systematic work, to obtain a systematic way, we need to just convert all arguments into something very easy, let's say. And we say that a persistent module is indecomposable if it is written like that. M is isomorphic to M1 direct sum M2. It automatically implies M1 on R2 is a zero persistent module. And we are defining an interval module, which is shown like K sub I. Again, it is a persistent module, as you can see. It's a collection of M sub i's, but it must satisfy two conditions. As a first, if your index is from your interval, then M sub K will be equal to K. K is shown as fields. Okay. From now on, I will work on fields instead of general commutative ring, because of because to use our structure theorem. And if your index is not from your interval, then it will be equal to 0. And what about the inner homomorphisms? If your two indexes, K and L, are coming from your, let me say, interval, then phi KL will be equal to the identity map. And otherwise, it is just 0 map. So these interval modules, you can consider like our basic structures. And we will try to represent our former actually theorems, structure theorem in terms of interval module. And as a good new interval module is indecomposable. So this is why it is our basic structure. Now, by using structure theorem and finite type arguments, a persistent module of finite type, let me say indexed by n and over k is something important. It can be isomorphic to the direct sum of interval modules. So if you have a persistent module satisfying these conditions, then you can write it as a direct sum of interval modules. Here, as you can see, intervals from left closed and from right open. Left one is an element of natural numbers. Right one can be also infinity. Now, let me just go back to my previous question. What was about the general case, which is, let me say, pointwise finite dimensional case. It is a bigger part of, let me say, actually, finite type persistent modules is a part of pointwise finite dimensional ones, because as you can see, only condition is the following: dimension of each mi is just finite. And as a good new, we can decompose pointwise finite dimensional persistent modules as well. But their proofs are coming from different ways. In the proof of this theorem, I guess quiver theory is basically used. And it says the following: if you have a persistent module indexed by t, then it can be written as a direct sum of intervals as well. And here, one of the very crucial things is just the set of intervals. Here, I is the set of Bn, as you can see, and this is a unique set, a unique multiset, let me say. And this unique multiset is called as barcode, the barcode of M. And this is a complete invariant in one parameter. So if you want to say two persistent modules, actually 2.5 finite dimensional persistent modules are isomorphic or not, you can use our barcodes. You can just pass through the barcode and try to see whether they are isomorphic or not by looking your barcodes. We will see a concrete example in a minute, but before that, we have another invariance, which is something equivalent to the barcode, which is defined as persistent diagram. You can consider it like this. We have, let us say, in the decomposition of our persistent module, we have some interval module where your interval is from 1 closed, 3 open, let us say. If you have something like that, then you are just going through your extended real plane. Then you are just putting a point at the point 1, sorry, I said 1 to 3, I guess, 1, 3. You are just putting a point in that 2 points to, let me say, boundaries. As you can see, we draw a point at I, j if there exists a p-dimensional class that is born at ki and dies at kj. Born means first appear, and die means it just merged with another one. Now, as an example, as you can see, we have a topological space M, and we are defining a function. Our function in this case is just projection onto the z-axis. Okay, as you can see, we are just taking projection onto z-axis. And we are defining a filtration, as in this case, you can consider like inversing it. You are considering from -infinity to some value. For example, from -infinity to here, there exists nothing. There exists nothing, so we don't have a topological space. But for example, if you consider this way, from -infinity to here, you are just starting your topological space. And when you just go up, let me say, and it's just getting bigger and bigger. So in each step, by taking a bigger z and considering the inverse image from -infinity to that set, you can obtain a filtration. And by applying homology, you can detect now our homology classes, our holes, let me say. And for instance, in this case, let us focus on the zero-dimensional homology. Zero-dimensional homology means number of connected components. The first one will appear in here, right? Because as you can see, from down to here, our topological space starts in this level. Now, so there will be a bar starting from here, and another bar will start in here because we have another connected component starting from here. But as you can see, those two things are just merging to each other in this level. So as you can see, we are just ending one of them. How we can decide which one to end? We have a well-known rule, which is called Elder rule. It says that if your two classes are merging, then just keep the one which born earlier. In this case, this is born earlier, so we are just keeping it. And this one is just starting from here and ending from here. As you can see, this bar is something finite, and this bar is just goes always because this is our one connected component. There exists no, actually, after some time, there exists no, actually, let me say, we can see this component always. That is something meaningful. So this level implies the infinity level. So it just starts in here and goes to infinity. So this is in terms of zero homology. In terms of one, you can see directly, this is something similar like torus. So you have sigma 1 and sigma 2 one-dimensional classes. Sigma 1 just starts in this level. So it will be in here, and sigma 2 is just starts where this whole is completed. So as you can see, it will start in here, and they will always live. Like there will be no dying time for them. So they will just appear always. And what about sigma 3? As you can see in here, we have another one-dimensional whole appearing first time in here. But as you can see, this part is just closed. We have some curvature, and then it just merging with here. So the sigma 3 is just dies in this level, let me say. So I said that our barcode is complete invariance in between 0.5 finite dimensional persistent modules. So if you consider an ordinary torus and this one, this topological space M, then their barcode will be different from each other, right? Yes, in the let me do it like this. In the ordinary torus, you will see this one, and this one, but you will not see these two bars, right? So by using that argument, we can say that in terms of persistence, this one and torus are something different. So if we go back, this can be a better discriminator than the other possible things in terms of data science. Okay, so it just is a very powerful tool. Now, in terms of persistent diagram, as I said before, this one born in here, so you are just finding the x value. Okay, let me use my in here. You are just corresponding to this one, and this is your x value in there. Let me just call this as x value in there. And then since it just goes to the infinity, you are just going to the x comma infinity points and just draw a point in there. So this is your point, corresponds to this long red line, let me say. And similar for the others. For example, in terms of this one, you are just going through here. This is your x value, and this one will be your y value. So you are just going and putting that point as in your persistent diagram. All right. So after this part, let me just continue with motivation of multiparameter persistent homology. All the things I just mentioned until now is just for one parameter. But there is a necessary question in this case, why we need to define multiparameter persistent homology. Now, let me just give a definition, just give an example to understand that one. Now, as you can see on the left up part, we have a data given discretely, and by depending on a, let's say, local density estimate. And as you can see, we have a circular shape in here, right? So if you just consider your general argument in terms of Viatori-Ritz complexes, and after that applying homology and passing to a barcode, you will obtain the below barcode in here. If you just apply one-dimensional homology. And that one-dimensional homology, as you can see, we have a long bar in here, right? This long bar just corresponds to this circular shape in here. So our one parameter persistent homology in here just detects that circular shape. Let us go to the right hand side. In here, we just add some outliers, some other points right in here, some outliers. Outlier means just some points which behaving different from the others, the general ones. Now, again, if you apply one-dimensional homology, then you cannot see such a long bar as you can see in here. We don't have such a long bar. Yes, we have some bigger bars in here, but probably they will just implying these possible circles in here. But as you can see, we cannot detect this one, but it is still there. We have density arguments, and if you consider, we have again from the density arguments, we have again a general circular shape in there, and also adding a few outliers change our barcode a lot. This is not something we want in persistent homology. So we say that one parameter persistent homology is not robust to outliers. So what is the possible solution? Just considering a second parameter. For example, in this case, you can consider a density parameter, which says that, for example, just don't consider points with density smaller than or equal to 10. So you will obtain exactly this one, this one. And if you just add those density parameter until, if you just, let us say, allow your density parameter just starting from 0 to something 50, let us say, then in each step, you will see this one and this one as well. So you are obtaining every possible data type in your given data. So with this way, we cannot, actually, we can obtain every possible barcode with ourselves. Okay. So this is why we are just passing through multiparameter persistent homology. Let me just define what about filtration persistent module in multiparameter case. I will just define them by using categorical arguments. We are saying that top will be the category of topological spaces and P be a poset. Then a P index filtration will be just a functor from P to top. And here, if your x is smaller than y, then the corresponding f sub x will be smaller than or equal to f sub y, actually as a subset of f sub y in here, as you can see. So again, if your index in your poset is getting bigger and bigger, then the corresponding topological space again bigger and bigger. And what about P? If you choose P as a cross product of TIs, where each TI is a total ordered set, then we call our filtration as a multiparameter or n-parameter filtration. Now, let me give an example, which is one of the general methods of obtaining filtrations. We have a topological space K, let us say, and we are obtaining sub-level set filtration. We will construct that. We are starting with our function from K to P. This is given for us. We have a function from our topological space to P, and we are considering a kind of inverse limits. We are just defining each spot of our filtration as in this form. We are saying that our filtration in the P spot will be defined as, will be made of from, let me say, K in K, such that f of K is smaller than or equal to P. So in each case, you will obtain, if you just take a bigger P, actually bigger element in the poset P, then your corresponding filtration element, corresponding topological space will be getting bigger and bigger. So in this way, you will obtain again a big filtration. So this is sub-level set filtration from P to top, and you can just understand that this is something very similar to inverse image arguments, but in the general case. Now, if you want to see a diagram of a multiparameter filtration from n cross n to k, then you can see it like this. We have f sub 0, 0, and we are going to this direction or this direction, and each map is just an inclusion map. Now, in one dimension, after we have one parameter filtration, we just apply homology. And in this case, again, the same. We will apply homology and we will pass through a persistent module. And in this case, we can define persistent modules in this form. A poset P, for a poset P, P index persistent module is just again a functor, but this time from P to vector spaces, category of vector spaces over some field K. as I said before, the reason which we are using our which we are working on our field is to obtain a better and clear, let me say, decompositions. And in here, each map for I is smaller than or equal to j, this var phi maps is just a linear map from mi to mj. And again, if you just take each ti as total ordered set, you will call as multiparameter or m-parameter persistent module. Now, we are passing through the decomposition argument. In one parameter, for finite type case, by using the PID argument of kx, which is polynomial ring over k, we can pass through the decomposition into interval modules, right? But this cannot be generalized to the multiparameter case, because in the multiparameter, you will obtain at least k of xy, which is a polynomial ring over two variables. But kxy is not a PID, so you cannot use structure theorem. So after that remark, we can consider what about PFT, pointwise finite dimensional ones. And we can say that we can still decompose pointwise finite dimensional persistent modules. And as in this form, let me say, each pointwise finite dimensional persistent modules of n parameter can be decomposed into this form. M is isomorphic to direct sum of m to the lambdas. Here, m to the lambda is an indecomposable as well. And this method is unique. What about if you have, if you decompose it into interval modules? By the way, it must be said into indecomposables. I guess this must be indecomposable, but I will check for that. If you decompose into two different ways, as you can see, then there is a bijection in between your indexes, such that the corresponding ones will be isomorphic to each other. So this says the uniqueness argument. This above decomposition is still unique. But the problem in here as follows. In one parameter, all of the m to the lambdas are just, let me say, interval modules. But in this case, they are just indecomposables. We don't know what they are. And without knowing what they are, we cannot say that this gives a complete invariant, this gives something else. And actually, we don't have a complete invariant structure in here. We cannot extend our barcode and persistent diagram to multiparameter. So this is a one bad side of multiparameter case. We cannot extend your barcode and persistent diagram to the multiparameter case again. So this just implies a question how we can compare the given persistent modules, for example. And the argument is we can compare them by considering distances. Here, distance means actually a pseudometric. Sometimes it is metric over some restricted categories, but generally we are saying that it is just pseudometric, actually extended pseudometric. And here we are defining like this. The first one is interleaving distance. We are defining over Rn index persistent modules. We are starting with an epsilon, which is a real number, positive or zero as well. Then we define a functor, shift functor, from m mod to m mod. M mod means the category of n-dimensional, m-parameter persistent modules. And if you just take an m and just let it to go to m of epsilon, then it will be just a shift of the previous one, the shift of m. And the I spot of m of epsilon will be the I plus epsilon vector spot of m. Here, epsilon vector means in each coordinate we have epsilon. And similar for the inner homomorphisms, inner linear maps. The new maps of m of epsilon vector will be just the maps from m from I plus epsilon vector to j plus epsilon vector. So we are just taking an m and shifting it with an epsilon vector and calling the new one as our shifted, let me say, persistent module. And again, for two Rn index persistent modules, we say that they are epsilon interleaved if there exist morphisms, phi and psi, satisfying these commutative diagrams. Here, phi from m to n epsilon and psi from m to m epsilon. So we are just trying to obtain these diagrams as commutative. Okay. By the way, here morphisms means just natural transformation. So again, we have actually the parallelogram diagrams as well. And now we just defined epsilon interleaved. Epsilon interleaved, as you can see, how far from they are being isomorphic. It just detects that one. If you just give two persistent modules, it tries to understand how far from being isomorphic. And now, by the way, isomorphic means zero interleaved in this case. If you have two persistent modules which are zero interleaved, then we can call them as isomorphic. And we can define interleaving distance is in this form. We are considering all the interleavings here, epsilon interleavings, and we are just taking the infimum of all epsilons, and we are saying that this is our interleaving distance. And now let me define something new, stable distance. We want a distance to be stable. Stable means if you just start with two functions, let me say in here f and g, if you just start with two functions f and g, and if you just perturb one of them, let me say f, and obtain g by perturbing one of them, as you can see in here, if you just perturb f and obtain g, so that means the distance between them is something smaller, right? Then your corresponding distance must be smaller than that. So if you just perturb your functions a little bit, then the corresponding distance will be smaller than or equal to that. Okay, so we are not allowing big differences in our distance arguments. Now let me just give a clear definition. Let us say we have a distance which is extended pseudometric. We say it is I-stable if we have this comparison. In here, we are just starting with function f and g, and we are considering the L infinity norm in between them. That means we are considering, okay, in this level, we are considering the difference, and we are taking the maximum in each coordinates, maximum of the coordinates, let me say, and we are doing this for all x in x, and then we are considering supremum. This is L infinity norm. And if you have two functions f and g, which are sublevel functions, actually sublevel set filtration functions, then we can pass through sublevel sets, and by applying I homology, we can obtain the corresponding persistent modules. And by considering the distance between these persistent modules, we can obtain our distance argument on the left-hand side, hopefully. And if we obtain on the left-hand side, we call our distance as stable. Now, we call actually I-stable in this case, and to say it is stable, we need to obtain this comparison for all I bigger than or equal to 0. Now, as an intuitive idea, we want our metrics, our distances, to be stable. This is something we want. And in this case, interleaving distance is stable. And we can show it like this. If you just start with allowing, actually letting supremum in here, L infinity, as epsilon, then your corresponding sublevel set filtrations will be epsilon interleaved. That means S of f, which is the sublevel set filtration obtained from f, will be inside of the sublevel set filtration of g with an epsilon shift, and similar for the other. As I said before, actually, I just defined epsilon interleaving in between persistent modules, but this can be generalized to any category, I guess. And for example, in this case, I just defined it for filtration, the category of topological spaces, let's say. And these two inclusions gives an epsilon interleaving between sublevel set filtrations. And if we apply homology to these filtrations, then we obtain an epsilon interleaving between the corresponding persistent modules by using the naturality of homology factor in this case. So this says these two persistent modules are epsilon interleaves, but as we will remember, the infimum of all epsilons gives the interleaving distance. So if you have epsilon in here, this part will be the infimum of all possible epsilons. So you will obtain in the interleaving on the left-hand side. So that means interleaving distance is smaller than or equal to supremum always. So interleaving distance is stable. Now, let us move on to a new distance argument. The problem, before going into detail into this one, the problem of interleaving distance is it is hard to compute. Actually, it is NP hard. I'm not very familiar with terminology in this case, but it is very hard to compute. So we are looking for other distances, and I will define for one parameter the bottleneck distance. It is defined as in this case. We have two barcodes. What was barcodes? The set of intervals, as you will remember, and we are defining a matching. Here we just match I with J. I is coming from the first barcode, J is coming from the second barcode. Here every element in these barcodes can occur in the matching at most once, and if you don't see an element, it is called unmatched. Okay, so after these remarks, we can define a cost. If I is matched with J, then we can define its cost as in this and is in the following way. Here I is the interval from AB, J is from C to D. You can ask that why I am using such a brackets, because it can be open or closed as well. Because in the R case, in the general case, real value, in the R indexed persistent modules, the left part or right part can be closed or open as well. So I am choosing to use like that. Then the cost will be the maximum of the difference in between x coordinates and y coordinates in the absolute value. And if AB interval is unmatched, then the cost will be B minus A over 2. Then we are calling the cost of the whole matching as in this way. We are considering the supremum of all costs of matched ones, the supremum of the cost of unmatched ones, and then we are calling the whole maximum of that one as our cost. And then we are calling the infimum of that cost as all the possible costs, let me say, as the bottleneck distance. And now the good side of one parameter, the interleaving distance and the bottleneck distance are equal to each other for 0.5 finite dimensional persistent modules. Now let us try to understand how we can just obtain a multiparameter argument for a bottleneck distance and whether they are equal to each other or not. We have a similar definition in terms of bottleneck distance. Again, we have two, I will not say barcode, but multi-sets of intervals, I will say. We will define a matching again in the same way, and we are calling a matching as epsilon matching in between C and D, as in this form. If these three conditions are satisfied, for all matched ones, the interval modules K sub I and K sub J must be epsilon interleaved. And for all unmatched ones from I and C and J and D, the corresponding interval modules K sub I and K sub J must be epsilon interleaved with the zero module. And the bottleneck distance in the multiparameter case is defined as the infimum of all epsilons. And these two definitions I give in one parameter and the general multiparameter case are equal to each other in one parameter case as well. So no worry for them. You can ask that why we are using the other definition. The answer is because, as you can see in here, it is all computable. It is all computation, right? We are just defining some cost and we are considering supremums, etc. So it is an easier method to compute the bottleneck distance. And now, yes, we have a similar question. Isometric theorem means in one parameter the equivalence of interleaving and bottleneck distances. But we are asking that right now, is it true for multiparameter case? And the result of Bijarkevich says that if you just take your barcode of M as I1, I2, I3, I1 is this one, I2 in this purple, and I3 in the middle one, and J is the red one, as you can see. If you just consider your intervals as in this one, and you just pass through the corresponding interval modules and consider the interleaving distance and bottleneck distance, then they will not be equal to each other. So this says that in one parameter, yes, they are equal, but in multi-parameter case, they are not equal to each other. And this is something we didn't expect, except maybe, I don't know. Except is not true, I guess, but this is not something we want, at least like that. All right, now as a last distance argument of this talk, we will define matching distance. I defined in interleaving distance. Interleaving distance was stable, but it is hard to compute. Bottleneck distance in one parameter is perfect. It is equal to interleaving distance, so it is stable in one parameter, and it is easy to compute. So that is good. But for multiparameter case, bottleneck distance is not stable over prime fields. Let me say, I will not go into detail, but it is doesn't complete our expectations. So we are trying to find a computable surrogate of both of them, and that one is the matching distance. The basic argument is the following: we want to use the computational arguments of bottleneck distance in one parameter. So if we start with n parameter persistent module, somehow if we just restrict that persistent module to a one parameter persistent module, then we can use the arguments of bottleneck distance, and we will use that to obtain our, actually, we will do that argument by considering lines in Rn, by restricting our persistent modules to lines in Rn. So let L be a line in Rn with this direction vector. And so the equation will be like this: U is equal to Tm plus B. Here T is in R, B is just an Rn element, which is an arbitrary point on the line. So if we let our direction vector takes values in positive real numbers, then we say that this line is admissible line. And now, as I said before, if you start with a persistent module, m parameter persistent module m, then by restricting that m to this line, we will obtain ml, which is a one parameter persistent module. And the restriction is as follows: ml in the I spot is defined as n sub u. Here u is im plus b. As you can see, I is an element of real numbers, but u is an element of Rn. So that means we just restrict our m parameter persistent module to a one parameter 1. And similar for the inner homomorphisms as well. So after this restriction, we can define matching distance as follows. It is defined over 0.5 finite dimensional persistent modules. We are considering the restricted ones, ML and NL, and we are considering their barcodes, and we are just computing their bottleneck distance. And we know it's something easy. And we are multiplying this with ML. ML means minimum of all m sub i's, all coordinates of the direction vector. We are just taking the minimum. And we are just doing this for any admissible line L. And we are considering this supremum as our matching distance. In here, L varies in the set of admissible lines. But we know that there are infinitely many admissible lines. So this is nothing very easy to compute. And as a final remark, let's say, instead of for an admissible line, we can obtain different parameterizations, and for different parameterizations, we are obtaining the same matching distance. So instead of the set of admissible lines, we can restrict that set to some other set, which is the set lambda with 2 or 3 more properties. Here we are just restricted m takes values from 0 to 1 in each coordinates, and with respect to max norm, it says in here, and the additions of the coordinates of B, which are additions of BI's, is just 0. With these restrictions, we can say that every admissible line has a representative in this set, and every line in this set is determined by M and B uniquely, and the result of this multiplication in the computation of matching distance is always same for different parameterizations of the same lines, same admissible line L. So that means the restricting the set of admissible lines to this lambda set changes nothing. So we just get rid of from some lines. But in here, again, we have infinitely many lines. So this is an active area to work. There are some new papers to compute the matching distance by looking finitely many lines there, let's say. Okay. Now, as a final, we are trying to understand whether the matching distance is stable or not. And there are two, I guess, one theorem and one lemma of Claudio Landi. She introduced that if M and N are epsilon interleaved, then the restricted ones, ML and NL, are epsilon over ML interleaved. And the second says that for pointwise finite dimensional persistent modules, matching distance is always smaller than or equal to interleaving distance. So that says that matching distance is also stable. So this is something we want. And as a proof of this one, you can consider it like this. From the above lemma, this says that ml times di of the interleaving distance of the restricted ones will be smaller than or equal to interleaving distance of the n parameter persistent modules. Here we know that ml and r pointwise finite dimensional, so ml and nl are pointwise finite dimensional, and they are one parameter case. So instead of this di, I can just go and write the bottleneck distance, right? The corresponding bottleneck distance. So as you can see, in the definition of the matching distance, we have the bottleneck distance in here. So you can see they are actually equal to each other in one parameter. And we are just considering, in each case, it is smaller than this one, and we are considering the supremum. So all in all, again, it will be a smaller than or equal to the interleaving distance. So the matching distance is just smaller than or equal to interleaving distance. So it is something stable. And as I said before, this is an active area to find how it is computed, how the matching distance is computed. So that's all from me. Thank you for listening. I hope it is a good starting to the topic. I hope you enjoyed all. Thanks.
So should we say thanks? Oh, sorry, Zach.
Thank you.
And any questions?
Sort of have one. I'm not really sure how to formulate it yet, but like, yeah. So I'm just kind of wondering about like how computable these things are. If you have like some actual data set and you want to like go and compute some of these distances. One is like how explicit can you make a persistence module? You know, can that be coded up in some finitary way? And then two, how like can you compute these distances that involve suprema, right? Because computing a soup can be hard unless you have like a finite set.
Yeah, you are. I understood. There are some let's say programs. I guess RUET, one of them. Michael Lesnick and his colleagues are just made a program which computes the corresponding persistent module in multiparameter case, and then you can just again, I guess, find the barcode in one parameter. So in practice, they are very good to obtain. I guess its name is RUET. I am not very fully convinced with the computation part in the general case, but I know that matching distance is computable in polynomial time. I guess OM2, it's computed in such a form. And it is something, I guess, 2 or 3 years ago, it's just founded. I know that interleaving distance is MP hard to find. So this is why we are looking for some other distance, for instance, the appearance of the matching distance as well. And but by the way, the matching distance in similar kind of persistent modules, multiparameter persistent modules, is something easier because we are just correspond to the bottleneck distance, and the bottleneck distance is just in the one parameter, just the computation, as you will remember. We have some intervals, then we are just considering some supremum, so it is not very hard to compute.
Yeah, that's great. Thank you.
Any other questions? I guess I have a question about this epsilon that you talked about at the very beginning with the as epsilon got larger, the points got more. Is there like, I guess some kind of exactly this Is there some kind of like industry standard for because I know you said there is no best epsilon, but I presume from a practical perspective you'll need to have one. So it's like an industry standard way of choosing where the sweet spot, for instance, in these images are.
Yeah, understood. Yes, actually in some cases there can be the best epsilon. I can accept that in terms of the distance, but the argument in terms of the data, but the argument is the following: the idea of persistent homology is just tracking all of the possible epsilons, because we are trying to see some homology class just appears in here and just have some lifespan and it just dies in here. So instead of focusing on the sum epsilon, we are considering all of the possible things. And again, in terms of some, I guess, big holes and small holes, I said something like that. And they are in terms of internal importance. And somewhere, for instance, in here as well, as you can see, we have some small hole, let me say, and a big hole appears in here for the first time in here, but the small hole just disappears. So for this data, for instance, the best epsilon, I guess, is not very, very, very meaningful. I don't know, because maybe you can say that, yes, this is rather getting nearer and nearer to each other as we just obtain a small epsilon, and these ones are just getting outer and outer, not outer and outer, but they are far from with respect to these cases. So you can say maybe this one the best, but as I said before, this is not the aim of persistent homology. Maybe that's kind of arguments can be studied as well, but I don't know.
Yeah, I actually have a related question, which is like, if you're actually doing this in practice, you have the epsilon you're ranging over, but then you have kind of like another epsilon, which is like the step size. Like, how much do you actually increase your epsilon each time? And I wonder, in principle, like if you make it too big, right, you could like miss an entire birth and death of a whole, right?
Yes.
Yeah. So how do you choose the second epsilon?
I guess, yes, you are totally right. We don't want to actually, we want to consider all of the possible epsilons. That's why we are considering like that. But for instance, in the discrete Morse theory, I guess there are some arguments of critical values that says where homology changing. So if you know where homology changes, then by specifying some points, you can deal with it. So that's also actually relax our job, right?
So yeah, any more questions? If not, should we thank Uğur again?
You're welcome. It's my pleasure. Thank you for doing this.
And then I'll stop the recording.